Okay, here's my thinking on the AP Physics review number 8. After doing this question, I think that this is a perfect question for review because this is exactly what the AP test is going to try to do. If you did this question, you realize that they started with one content area and then they just switched. Throughout the entire question, they covered about 4 different topics, and that's exactly what I think the AP test will be like. So they started with a sphere attached to a string that's attached to a ceiling with an angle from the vertical of theta, and the sphere is moving in a horizontal circle about around the center of that circle as c with a radius of r. So when I saw this question, I was thinking about our flying pig lab because it seems very similar. So the question starts with 2 student claims. The first student claims that the sphere cannot be accelerating towards the center of the path because none of the forces are directed towards the center. And the second student claims that the tension is less than the weight of the sphere, and therefore it must be accelerating down. Okay, so they want us to identify what's wrong with both of those claims. So for student A, I do believe that there is not necessarily a force directed toward the center, but definitely a component. If you think about the forces acting on the sphere, we have weight acting down, or mg acting down, and we have tension acting up. And tension then has 2 components. So if you think about tension here as a vector, it has two components, a horizontal component, and it's got a vertical component. So I think student A is wrong because there is definitely a horizontal component of tension that does act towards the center of the circle. And for student B, student B said that the tension is less than that of the weight. I disagree with that. I think that the vertical component of tension is equal to the weight. Again, the sphere is accelerating toward the center of the circle. It's moving at a constant speed around this center of the circle, so it's not accelerating up or down. It's accelerating inward toward the center. So the upward force of tension must match that of the force due to gravity, or the weight of the sphere, which would make the tensional force larger than the weight, since the tensional force is the hypotenuse of this triangle that's made by the weight, the horizontal component of tension, and then tension itself. Okay, so that was A. B wants us to derive an expression for net force. So there's 2 ways we could have approached this. We could have said the net force is equal to ma, where A equals v squared over r, and we have r, but we don't have v, and they don't want v to be part of the expression, so I don't think that this is the proper approach. The other approach would be to solve it in terms of the forces. So the net force is this force right here, this force that's acting toward the center of the circle, which if we look at our triangle that we formed here with tension and the horizontal component of tension here, which is our centripetal force, and then our vertical component to be the weight of the sphere. So what we can see here is that we're really solving for this component of this triangle. So I know theta, and I know that this side is opposite of theta, and our other known side is the weight of the sphere. So I can say that tangent of theta equals the centripetal force, the net force, over mg. So I started with this expression here, and then I just rearranged it for centripetal force, which is our net force, which gave me tan theta mg. And that was B. And then double I just wants us to go back and show where does our thinking match up with student A and student B's correction. So with student A's correction, I talked about how the horizontal component of tension is toward the center. So that was the first part of my derivation, saying that, hey, this is the side of the triangle that they're looking for. So this is the centripetal force. So that started off my expression with the net force being the centripetal force. And then the other student said, made the comment about the upward, or about tension being less than that of the weight, where the tension's actually greater than the weight, where the upward component of tension, the vertical component, is equal to the weight. So that's where we've corrected student B. So the upward component is equal to weight. The horizontal component is the net force, and we know theta, so we rearranged it and we got this. Okay, then they change gears and they say that the sphere is now acting as a pendulum, so it's not moving in a circular path, it's just moving back and forth like a pendulum. So that reminded me of our pendulum lab. And they gave us a graph with data that was period squared against length of the string. And I went to the equation sheet and I found the expression for period of a pendulum being 2 pi times root L over G. So first thing they wanted us to do was take these data points and draw a best fit line. So I did that, just drew a straight line, trying to represent the pattern of the plots. And then I thought about the slope. I thought about the slope being the rise of, I found it to be about 1 second squared for the rise, and the run to be about 0.2 meters. And I thought about how that slope might help me with this to find G. So they want us to use this graph to find G. So I rearranged this to solve for G. So solving for G, I would square each side, and that would give me what? G equaling 4 pi squared, and then that would give me L over period squared. So rearranging this for G gives me 4 pi squared times L over period squared. Well, I have period squared, and that would have been my rise of 1 second squared. And I have my L, that would be my run of 0.2 meters. So I just inserted 4 pi squared times 0.2 meters over 1 second squared. And it should have been in the ballpark of about 9.8, but honestly, the way I eyeballed my graph, I think I got something less than that, but it should have been around 9-ish. Actually, I guess we could go ahead and crunch this real quick. We got 4 times pi squared times 0.2. Yeah, I guess I did. I got something close to 9.2 meters per second squared, so not too bad. All right, so that was C. D. Okay, so D, they're asking us about an energy question. So they're giving us this graph here, and they're saying that this is the angle against time for the pendulum. So I drew this out, and I was thinking about how the pendulum would produce this type of graph. So at a max angle, I would say that our pendulum is at its maximum displacement from the vertical. And then here on the graph, our pendulum would be straight up and down. Here on the graph, it's at a max angle, but in the other direction. Here on the graph, we're back to straight up and down, and then here we're back to our original position. They want us to take this graph and create a energy graph, a potential energy of the system. Well, we know that the potential energy is highest when our pendulum is in a position when it's furthest away from the vertical, and it's lowest when it's at the vertical. So the potential energy of our pendulum is maxed at 3 positions. So here's my graph. So I'm thinking at our starting position, we have a very high potential energy. Also, when it's at its maximum vertical in the other direction, and again, back at the start. And then it's at a minimum potential energy at the points where it's just completely vertical, where theta is 0. So here's my graph of potential energy of the system, of the pendulum Earth system as time goes on. And then E changes gears once again and talks about rotation. So it's saying that as the sphere moves through the different positions in its pendulum motion, it must be rotating, and it must be rotating clockwise as it swings to the left, and it rotates and then that's clockwise, and then counterclockwise as it goes to the right. So they're asking when it's at this position right here, its maximum rightward position, in which direction would torque be applied? So I said clockwise. And the reason why I said clockwise is because at this position, if it's rotating clockwise as it moves from here to here, and therefore as it moves, actually it's going clockwise, it's rotating clockwise the entire time it moves to the right. It's rotating counterclockwise as it moves to the left. So at this position, it's changing its direction, or it's changing its rotational direction from rotating counterclockwise to rotating clockwise. So its torque must be clockwise. So again, it's rotating counterclockwise as it moves to the right, and it's rotating counterclockwise or clockwise as it moves from right to left. So at this position right here, it's changing its rotation from counterclockwise to clockwise. So it must have a clockwise torque at that position to create that change in rotational motion. All right, and that was it. That was my thinking on this AP Physics 1 AP exam review.